Welcome to our second podcast in this module, and with this lesson we'll be looking at the wave-particle duality of electrons, which essentially allows us to have a better understanding of the behavior of electrons. And then we'll also be looking at or describing the movement of electrons through what we call a wave function, and relating the wave function that the electron has in terms of its motion with respect to the energy that it has through what we describe as the Schrodinger wave equation. Now let us do a bit of a review of what we've learned so far. We should know that the electron is a fundamental particle of matter. It's a subatomic particle, and it has wave-like properties as demonstrated by experiments carried out by Thomson and Millikan. And then we were introduced to the first real model of the atom, which was Thomson's model, which basically shows that electrons are evenly distributed in a positively charged cloud. Then we went on to looking at a more sophisticated model of the atom as proposed by Rutherford, which shows that electrons are orbiting the nucleus at the center, and the electrons in themselves are in specific orbits around the nucleus. The problem with Rutherford's model, however, is that if we were to consider his model as is, if one were to irradiate a sample of gaseous hydrogen, then there would be the production of a continuous spectrum, which would indicate the continuous loss of energy as the electron is spiraling into the nucleus. And so, because of the fact that that didn't occur, in fact what occurs is that there is the observation of a line spectrum. Then there was need to have a better description of what the model is, a structure of the atom is, and that model was proposed by Bohr, which essentially explains how a line spectrum is produced by heating gaseous hydrogen. The proposal shows that the electron essentially is positioned, or is actually circulating or orbiting the nucleus at specific distances from the nucleus, and it loses energy or gains energy, thereby giving off a quantum of energy on transition from one energy state, or from one energy level or one orbit to another orbit. And this in effect is described through the process of quantization, where the electron, or the concept of quantization, where the electron orbiting the nucleus has specific energy, specific location, and specific momentum. However, as we had pointed out in the lecture, if we were to consider an atom that has more than one electron, then there will be other effects on the position of the electron, particularly because of repulsion, electron repulsion, and that would impact the movement of the electron, the position of the electron, and that essentially is incorporating a degree of uncertainty in defining exactly where the electron is, because of those electron repulsions, and as a result, the Bohr atomic model fails to explain the presence or the observation, or the kinds of emission spectra that atoms and ions with more than one electron have, and also the effect of magnetic fields on these emission spectra, and therefore doesn't clearly show any experimental evidence of why it is, or how it is, that an electron can travel in a circular orbit that is of a specific distance around the nucleus. And so the questions that would arise from that then, from that inadequacy, from that uncertainty, is how does one know the exact position of the electron, and how does one know the exact angular momentum of the electron according to Bohr's model? And because of the uncertainties that there are with respect to this model, then there's need to find a more sophisticated model for describing the atom, and that really requires the development of what was described as quantum mechanics, which basically incorporated two concepts, the concept of wave-particle duality and the concept of uncertainty, or the uncertainty principle. The wave-particle duality, if we think of the models that we looked at, let's say the Bohr model. The Bohr model has not yet incorporated fully the link between the particulate nature and the wave-like nature of the atom, of the electron, sorry. And also, the uncertainty arises because of the different kinds of interactions that would occur and how that would impact the position of the electron as it is orbiting the nucleus, considering as well the fact that the particle is wave-like. And so in this lecture, we want to set as a basis this idea, this concept of quantum mechanics, and show how it is that this idea of quantum mechanics is developed through the ideas of the wave-particle duality of the electron and the Heisenberg uncertainty principle, and then move on to describe the wave motion of the electron through what is described as the wave function, which incorporates the wave-particle duality feature of the electron as proposed by Schrodinger, and then look at a situation of the electron in a particular confined environment. Look at how it is that the wave function, which describes the motion of the electron, how that changes, and what information we can get from the wave function that tells us where it is that the electron can be found outside of the nucleus. And then introduce this idea of probability or probability density, where we look at the interaction of more than one or two wave functions, which again describes the motion of the electron, and what it is that the probability of the interaction of these wave functions tell us about the probability of finding an electron within a particular confined region of space. And then to essentially solve the wave function by linking the wave function with the energy that the electron has through the Schrodinger wave equation. I must ask to be pardoned because I'm actually not feeling well. I have a flu. As you can probably notice, I'm very nasal, and from time to time I might cough or sniffle. So I'm just asking to be excused because of that, but I still have to produce this podcast. Excuse me. Excuse me. Alright. So, what is this wave-particle duality of the electron? What do we know about the electron properties? Well, through experiments such as the cathode ray tube experiment, we saw where the electron outside of the atom, or outside of the cathode, behaved as light. And so we basically have summarized that the electron has wave-like properties. But through experiments carried out by Millikan, we saw that the electron has a mass and therefore is a particle. And so clearly the electron has two properties, and how it is that we can actually combine these two properties and get some information about the behavior of the electron based on these two properties as combined. As it relates to the particle properties, one can recognize that because of the associated mass that the electron has, there is a particular momentum that the electron has if it's moving with a particular velocity, and there's an associated energy. And as it relates to the wave-like properties, the electron is moving as a particular wave, therefore it has a wavelength, it has frequency, and it also has energies associated with it, with the movement. And of course, one can another important property that the electron has that pinpoints its wave-like property is the the diffraction that electrons can go through, which is based on the interference of the waves that the electron is moving with, or as I should say. And here is a depiction of the diffraction of electrons. The experiments were carried out by Davison and Garmer in 1927, and they basically directed a beam of electrons onto a nickel crystal, and the nickel crystal basically caused diffraction essentially. And when the waves when the diffracted waves interacted, they underwent constructive interference, which resulted in bright bands, and destructive interference, which resulted in dark bands. So again, this is direct experimental evidence which shows that electrons in fact are wave-like, because they underwent, or they actually are able to exhibit interference, both constructive and destructive interference. And this property and this kind of experimental evidence we want to actually get back to when we actually start looking at the wave function of the electron a little later on in the lecture. So how can we show then in one expression both the particle and wave properties of an electron? That idea was proposed by this fellow called Louis de Broglie in 1924. We recognize that if we consider the electron as a particle, there is an associated mass, and if we consider the electron as the electron as a wave, there is an associated mass with a wave motion. And so combining those two ideas born through Einstein, where we look at the energy of the particle, where E is equal to mc squared, and by Planck, which looks at through the wave property, shows the energy is equal to h nu. If we were to equate both energy values, right, we would see that h nu is equal to mc squared, and that then equals to be equal, and that then turns out to be h nu over c is equal to mc, where mc is equal to mass, which is mass times velocity, which is equal to momentum. And so we clearly can see in this one equation called the de Broglie wave equation the relationship of momentum and wavelength, where momentum incorporates the mass term and wavelength is an inherent property of a wave. And so we can clearly see that the de Broglie wave equation essentially describes both the wave and particle nature of small particles, and in this case the electron. Now this wave-particle duality is critical in us understanding the energy that is associated with the electron as it is moving within a particular confined space. Now, if we consider this wave-particle duality, or if we consider the wave-like motion of the electron, can the Bohr's model where the electron is confined to moving in a fixed orbit be correct? Well, let us look at this example here. Here we have an orbit, and this is according to Bohr's model. The electron is moving along a fixed orbit. But we can clearly see from this, if we were to superimpose a waveform or a wave motion over the orbit, it shows us that at a particular point in time or space, that the position of the electron is going to be different. For example, if it is here, this is one position, but if it is here, it's at another position, and so on and so forth. So this is basically telling us that that one cannot confine the electron to a fixed orbit if we have to consider the fact that the electron is moving as a wave. And this is showing us directly that the Bohr's model, even though it works for hydrogen, the electron in hydrogen, because the hydrogen atom is just one electron, it is simplistic. It's okay. It works to an extent, but it is inadequate even for hydrogen, because the Bohr's model has not considered the fact that the electron is moving as a wave. And so the question then is, can the behavior of the electron be predicted precisely? Can the motion of the electron be predicted precisely? Can the position or the location of the electron predicted precisely? And this idea of precision is very important, because yes, we might be able to predict or determine the location of the electron, but precisely how accurately, how precisely can we do that? And this idea of the uncertainty in describing the location of the electron, the position of the electron, was proposed by Werner Heisenberg, which basically, and the principle basically says that both the position and momentum of a particle cannot be determined precisely simultaneously. In other words, if we know the position, then we cannot know if we know the position very accurately or very precisely, we cannot determine the momentum very precisely both at the same time. Okay? And before we go into exactly what the Heisenberg uncertainty principle states, we want to actually present an analogy of what that is. This whole idea of determining position and momentum simultaneously, precisely. And I'm using here a game of pool, essentially, being played, and one takes a picture of the pool game at using a very high-speed camera. Alright? And then another case where you take a picture with a very low-speed camera. Now, if you use a very high-speed camera, the motion is frozen very quickly, you get a very sharp picture. Alright? The problem with that is that you can precisely determine the location, exactly where the balls are. Alright? But you have no sense of where the balls are moving. And if you have no sense of where the balls are moving, you have no sense of what the speed of the balls are, and you have no sense of what the momentum of the balls are. But if you use a low-speed camera, you will get a blurred image, and this is what we are showing here, an image that is blurred. What that shows us, and let us look at some examples here. Oh well. We can see that there's a trail, right, behind each ball. And if we look at this ball here, we can see that it was here, and it moved from here, and it moves in this line, and it's going in this direction. If you look at this ball, the trail is curved, and this gives us a sense of where the ball is going. It's going to move continuously in a curved manner. This again for this ball here, right? And in this case, this ball was here, and it's moving there. And so the blur seen of the ball, in this image taken by the low-speed camera, allows us to be able to determine, to a very great extent, the direction of motion of the ball, and it gives us a sense of what the speed is, because we can actually we should be able to calculate or determine the speed based on the distance traveled over a particular time. Alright? But rather, the location of the ball is uncertain. The fact that we are seeing a trail tells us that we don't know with any great degree of accuracy that the ball is exactly here. There is a large degree of error that is associated with the motion, with the actual position of the ball. And so these two cases are showing us that we cannot determine both the position and momentum simultaneously. In this case, we're able to determine precisely the position, but there is an uncertainty with determining the position, the speed and the momentum. And in this case, we're able to determine precisely, or with a great degree of accuracy, where the direction of motion is, but we are not able to determine with any great certainty the location of the balls. And so there is this uncertainty in determining both the position and momentum simultaneously. It is not to say that we cannot determine both the positions and momentum, but we cannot determine them both simultaneously with great certainty. And if we consider then the Bohr's model, Bohr's model is proposing that we know exactly where the electron is. It is confined to a specific orbit. Okay? And if we move from n is equal to 1 to n is equal to 2, we know at n is equal to 1 and n is equal to 2, those are specific orbits. Okay? Based on this uncertainty, it is telling us that we cannot know exactly where the electron is around the nucleus, whilst knowing exactly what the momentum is. And so the Bohr's model becomes inadequate in that regard, and particularly because as well it lacks any direct experimental evidence which tells us that that is the model. Now, so the uncertainty principle was, as I said, proposed by Warner Heisenberg, and he basically summed up his proposal in this hypothetical experiment here, where he wants to measure the position x and the momentum p of an electron by a gamma ray microscope. And the reason why he's using a gamma ray microscope is because let's just think of a normal light microscope. In order for us to see an image using a normal light microscope, we shine white light, and the white light interacts with the object, and we're able to see the image through the eyepiece. All right. If we think of an electron is so tiny, the wavelength is so small. As we can see, as human beings, we cannot see electrons because the wavelength of light is not comparable to the wavelength of an electron. And so in a hypothetical case, Heisenberg is proposing to use a gamma ray microscope where the wavelength of the gamma ray is almost equivalent to the wavelength of the electron, and therefore interaction of the wavelength of the gamma ray is able to allow for us to see through scattering of the gamma ray on interaction with the electron, for us to see the image. All right. So that is basically what we're trying to describe here. So he uses two types of gamma radiation. He uses a short wavelength gamma ray, and if we think of the association with wavelength and frequency and speed, if we have short wavelength, we have high energy, high frequency. We also have high momentum or large momentum. All right. So if we consider using the microscope with short gamma radiation, then what happens is that we will have large scattering. So let me correlate this analogy with this experiment with say two vehicles. We have a small car crossing an intersection, and we have a large trailer that is coming towards the intersection. And this large trailer is coming at very high speed. It has a large mass. It's moving with large momentum. And this small car, yes, is moving at a particular speed and so on, but it interacts with the car. It crashes into the car. What is going to happen is that the car is going to be in a perfect situation. It's going to be displaced to a large distance, all right? Because the truck is going to transfer its momentum towards the car, and the truck will essentially slow down because it would have transferred its momentum to the car, all right? And so the same thing is happening here. If the gamma rays with short radiation or large momentum is interacting with the electrons, there's going to be large scattering. The electron is going to be displaced to a great degree, and because of that, now we're able to now see a very sharp image of the electron, because the more scattering we have, the wider our field of view is, or angle of view is. in the microscope, and we're able to see a brighter image or a better, sharper image in the microscope. And so there's going to be a large transfer of momentum. But because there's a large transfer of momentum now, we don't know what the before and after momentum is going to be. And so there's going to be an uncertainty in the momentum. Because of the large scattering, we're able to see very sharply where the electron is, but we don't know what we don't know with certainty what the momentum is because of the large transfer of energy. And then if we look at a case where we have long gamma ray radiation, the long gamma ray radiation will have a lower frequency, will have a lower energy, and hence will also have a lower or smaller momentum. And so think again, going back to the analogy with the truck and the car, we now have, instead of a big truck hitting the car, we have we have a smaller vehicle hitting the car. It means that the momentum that vehicle is carrying is not going. It's going to transfer, but it's not going to cause a large scattering of or a large deflection or disposition of the displacement, I should say, of the car that it hits into. And so, in the case of the gamma ray interacting with the electron with small momentum, there's going to be small scattering, and there's going to be an uncertainty in determining, because the image that we will see from the microscope is not going to be very sharp. It's not going to be very bright because the scattering is small. Alright, but there's going to be a small transfer of momentum. And because there's a small transfer of momentum, the before and after momenta are more or less the same. And so we are able to determine more precisely the momentum of the electron, but we can't determine very precisely the position because we didn't have large scattering. And so in either case, we see that one of the parameters that we're measuring, either position or momentum, is being sacrificed. In one case, we're able to determine precisely one. In the other case, we're not able to determine precisely the other one. And that is summed up in Heisenberg's uncertainty principle, which says that the product of the uncertainty delta, meaning change or uncertainty in x, or the position, and p, the momentum, is greater than or equal to h over 4 pi. Alright, and this equation can allow us to be able to determine either the uncertainty in the position or the uncertainty in the momentum for a body that is moving at a particular speed with a particular momentum and so on. Alright, but what the principle states to us is that both the position and the momentum cannot be determined precisely simultaneously. And so, going back to our question that we asked before, considering the wave-like motion of the electron, can Bohr's model where the electron is confined to moving in a fixed orbit be correct? Considering the uncertainty that exists in determining exactly the momentum and the location, the model that Bohr proposes is very wrong, because the electron is moving as a wave, and it has a wave-particle duality, the behavior of the electron cannot be predicted precisely as according to the Heisenberg uncertainty principle. And so we still are left with the question, how do we view electrons in atoms? Clearly we have to investigate the wave-like properties, and hopefully that will allow us to be able to get a more definitive answer as to seeing how it is that the electron is moving around the nucleus. And the basis of that is what we describe, or what is going to help us to allow us to be able to do that, is this concept of wave mechanics. Alright, so what is wave mechanics? Wave mechanics basically looks at studying the properties of waves as a standing wave. What is a standing wave? A standing wave is essentially a wave that is essentially fixed at both ends, confined within a particular region of space. Alright? And this is a very simplistic example where we have a string that is attached to both ends of a piece of wall, and there's a specific distance between both, and we can pluck the string, and we can, depending on how strongly we pluck the string, the wave will vibrate at a particular frequency, alright, or different frequencies. Now, the description of a standing wave is such that we can describe the wavelength lambda in terms of this formula here, 2L over n, where L is the distance that the wave is vibrating within, or the region of space that the wave is confined, and in this case it's here, and n is a constant which changes. I shouldn't say constant, it's an integer which changes. It's an integer whole number which changes depending on the mode of, or depending on what the frequency is, the frequency of vibration. And so we see that there is a relationship between, and so if we know L and we know what n is, then we are able to determine what the wavelength is. And n effectively is equal to, or in fact n plus 1 is equal to the number of nodes. N plus 1, the integer n plus 1 is equal to the number of nodes. What are nodes? Nodes are essentially points along the wave that have zero displacement. So in this case, we have here one mode of vibration. At both ends here, we have zero displacement, right? Because we have the zero line. We have zero displacement at this end and at that end. We have two nodes, and therefore, in order to determine n, we can actually work that out, and clearly that shows us that n is equal to 1. And so, what is the wavelength? The wavelength lambda is equal to 2 times L over 1, right? 2 times L over 1. And we can try to visually see it. This is basically showing half of a wave, alright? If we were to have seen a full wave, we would have had to have done this, right? And so we are seeing that the wavelength is basically, in this case, the distance, 2 times the wavelength is actually going to be equal to 2 times the length of the confined space whenever the frequency is the fundamental frequency. Alright? The fundamental frequency, the lowest possible frequency that the wave can vibrate at. If we were to pluck the string at a higher frequency, or at a higher, we pluck the string stronger to cause it to vibrate at a higher frequency, the first, what we call the first overtone, or the second harmonic, or the vibration that is that comes after the fundamental, essentially shows us that there is this kind of vibration. Alright, and if we were to determine the wavelength, again, wavelength is equal to 2L over n, we see that the wavelength is equal to 2L over 2. Alright, we can cancel the 2's, and it ends up that the wavelength is equal to L. Alright, and this is basically what it's showing. Right, this is one wavelength motion of the string at that particular frequency. And then, if we were to pluck the string a little harder, the subsequent harmonic, which is the third harmonic, or the second overtone, is this, right? And we see that the wavelength lambda is equal to 2L over 3. Alright? Now, let me back up a little bit. We know that n is equal to 1. We saw where n is equal to 1 in this case, because the number of nodes is equal to 1 and 2, and therefore the n is going to be equal to 1. In this case, the number of nodes, we have 1, 2, 3 nodes. Nodes are points of zero displacement. And so, n is going to be equal to 2, because number of nodes is 3, and n plus 1 is equal to 3. And so n is going to be equal to 2. And in this case, we have 1, 2, 3, 4 nodes. And therefore, n is going to be equal to 3. And so, if we were to determine what the wavelength is, 2L over n, right, we end up with L lambda is equal to 2L over 3, which is essentially 1.5 times L. And right, and so 2/3 2L over 3. What am I seeing here? 2/3, right? 2/3, not 1.5. 2/3 of L. All right, and so we see that one wavelength, right, from here to here is essentially 2/3 of the entire distance L. All right, and and we can actually continue by as the vibrations increase or the frequency increase, we will see when n is equal to 4 that lambda is equal to what is that, 2L over 4, which is basically equal to a half of L. Okay, and we will now have 5 nodes, 1, 2, 3, 4, and another node which allows it to be 5. So we'll basically be seeing 2 wavelengths within that L, that region of space described as L. Alright? And so this is basically the fundamentals of wave mechanics. It's a wave that is confined to 2 ends that vibrate at various modes or frequencies, and the wavelengths are calculated based on this equation where it's equal to 2L over n, where n is an integer whole number. Now what do we know of, and we could actually have used x, y, and z instead of n, but we use it in here because we want to actually correlate directly this idea of quantization, which we met when we were looking at the Bohr's model, where n is equal to 1, 2, 3, 4, 5, and so on, which basically indicates to us that we have quantization of both position, momentum, and energy, and so on. So basically, a standing wave also depicts this idea of quantization, that it is that you can only have specific values of wavelengths, you can only have specific values of frequency, you can only have specific values of energy. You don't have any arbitrary values of wavelength, frequency, or energy, all because we're considering the vibration of the wave within a specific region of space, confined within a region as shown in this case. Alright? And so we can correlate the standing wave to the motion of an electron. And this idea of correlating the motion of an electron and describing the motion of the electron was proposed by Schrodinger in 1927. And he basically says that an electron that is traveling as a standing wave, essentially its motions, wave motion, can be described by a mathematical equation called the wave function, which is equal to the square root of 2L sine n pi x over L. And that wave function value, which describes the wave motion of the electron, is equal to whole number integer values 1, 2, 3, 4, 5, 6, and so on. Alright? When we look at the wave function, we clearly see n, and this is telling us that the wave function can only have specific values, and that's why we're there 1, 2, 3, 4. And this is telling us that the wave function is quantized. Now, in order for this wave function to be applicable, to be useful, the electron has to be confined to moving within a specific region of space. It's not any arbitrary region of space within which there are no boundaries. There has to be certain boundaries that limit the motion of the electron. And again, we go back to describing the motion of the electron as that of a standing wave. And here we are basically depicting that. It's similar to what we were showing on the previous slide, where when n is equal to 1, we have a wave function that is associated with the lowest possible frequency of motion. Alright? When n is equal to 2, we have one wavelength motion. Alright? And that is psi 2. And when n is equal to 3, and so we see that the wave function changes by a specific amount, by a particular value, integer value, based on the change in the principal quantum number n equal n. Alright? Now what is very important is that the wave function basically shows that because it has a sine function in there, basically describes distinctly the fact that the wave function is a sine function. It tells us that the electron is traveling as a wave. Alright? And so Schrodinger proposes that the electron that is traveling, but let me just go back again, and it also describes that it has this value L, which essentially is what we describe as a boundary condition, or the distance within which the electron is moving Alright, and those two ideas, or I should say, the idea that the electron is traveling within a particular space, in this case, we call a one-dimensional box, because L is shown as the length of the boundaries within which the electron can move, where x is equal to, from x is equal to 0 to x equal to L. Alright, and so this electron traveling in a one-dimensional box, and one dimension meaning along one axis, defined by the distance L, okay, is the motion is a wave-like motion, which is described through its wave function, which essentially confines the electron within a particular region of space and moving with respect to, or changes based on the principal quantum number n, and the wave function has integer values or specific values, thereby indicating that the wave function is also quantized. So what information does the wave function indicate about the location of the electron? Because that's essentially what we want to find out. Alright, so let us look at, in very direct terms, what the wave function tells us when x, the position, changes. Alright, so x here, so x basically is equal to 0 at this end, and is equal to L at the maximum at this end. Alright, and we know what L is. L is the total distance. Alright, we know what pi is, and we can actually change the value of n, and we can basically see what the psi, the wave function, changes. Importantly, we will see that this, because it's, and we should know that from basic mathematics, that a sine function can have negative, positive, and a 0 value. Alright, and we'll see that essentially. Alright, so if x is equal to 0, right, that is to say that x is equal to x, we are looking at x is equal to 0 right here at the start of the box. What is psi? Let us choose a particular quantum number n. N is equal to 2. Alright, so we plug in n in our sine function, and we have our L in our sine function, we have our x value in our sine function. So if x is equal to 0, then the whole term here becomes 0. Alright, sine 2 pi x over L is essentially equal to sine 0, which is 0. Alright, and as a result, if this is 0, then this is 0. So psi is equal to 0. And by the way, the wave function is described through this notation here, psi, which is a Greek letter. Alright, now if we were to increase distance, what if x is equal to a quarter of L, L over 4? Alright, which means that we're looking at quarter of the length of the box. Alright, if we were to now plug in what the value of x is, which is L over 4, or a quarter of L, then this term here, sine 2 pi x over L, now becomes sine pi over 2. Alright, the L's will cancel and so on. And sine pi over 2, you can plug that into your equation, you'll find out that that is equal to 1. If that is equal to 1, then psi turns out to be equal to the square root of 2 over L. Alright, and it's a positive value. Alright, now if x is equal to a half of L, alright, meaning that we're here, okay, then this sine part of this sine function becomes sine pi, which is equal to 0, and therefore if we were to plug that back into our equation here, then psi becomes 0. So let me back up. When psi is equal to 0, we are at x equal to 0. When psi is equal to the square root of 2 over L, we're seeing a maximum value. This is not really drawn to scale entirely, so but this is really supposed to be a quarter. This peak here is supposed to be right here, and we're seeing that we have a maximum value for psi. When psi is equal to 0, we know going back to the 0 line. Alright, and then when psi is equal to 3/4 of L, alright, which means that we're 3/4 the length of L. If we plug that into our equation, we end up getting sine 3 pi over 2 is equal to -1. and therefore psi is equal to minus 2L, or the square root of 2L. Right? We're seeing that this is the minima. So when psi is equal to a quarter, we're seeing the maximum value of psi, and when x is equal to a quarter, we're seeing the maximum value of psi. When x is equal to 3/4, we're seeing the minimum value of psi, a negative value. So again, that's showing us that the sine function psi can be positive and negative. When we go to the extreme end of the box now, x is equal to L, it turns out that psi is equal to 0 again. Alright, so what we clearly can see is that this sine function is describing the wave motion. If we change the value of x, we change the value of psi. And the fact that the value of psi, which describes the wave function, is changing as x is changing, is introducing this idea of uncertainty in determining exactly where the electron is. For a particular value of n, right, if you go back to our Bohr's model, if we have n is equal to 2, we are looking at an orbit that is at a particular distance from the nucleus, right? But in this case, based on the sine function, if n is equal to 2, we're seeing that because the electron is moving like a wave, the position changes effectively. Alright? And this wave function essentially is describing to us in more definitive terms with respect to the wave property of the electron, the likelihood of finding where the electron is in a particular region, a particular confined space, a particular boundary, in this case in a one-dimensional box. Alright? So let us summarize what the wave function is telling us about the electron. It is describing the wave motion of the electron. It tells us that it's a sine function, and therefore it tells us that that sine function, that wave function, can be either negative or positive. It has an associated principal quantum number n, alright, which basically allows us to have an idea of the possibility of where the electron is, alright. And we know that the energy that is associated, if there's a particular quantum number, then that quantum number is directly related to the energy of the system or the electron. Remember that equation that we met with Bohr, E is equal to m squared over h pi over 8ml squared, or something like that. That is linking the quantum number with energy, and so and we know that the momentum is also linked to energy, and so we see that the principal quantum number gives us an idea of the location, but it also gives us an idea of the energy and the momentum of the electron, and that these three are quantized. And also, if you look back at the wave function, there's a value of L, which basically describes the region of space, or the boundary, or the confines within which the electron can be found, essentially. So what we haven't actually done yet is to link directly, and I made mention of it just a while ago, is to link directly the to show how it is that the particle and wave motion as combined is also equivalent to, or gives an idea of, the energy of the electron. Again, if we have a moving electron, it has a particular kinetic energy. Ek is equal to half mv squared, which we can actually expand, and then we can show that it's actually equal to the square of the momentum, right? Half mv squared, okay, is basically equal to m squared v squared over 2m. If we cancel out the m, we end up with m v squared over 2, right? Which is basically what that is saying. But if you keep it in this expanded format, we basically are saying that we have m times v and n times v, so that is p squared, and m times v is p, so that is p squared over 2m. And so since the electron is traveling as a wave, if we utilize the Broglie, and it's a particle, if we utilize the Broglie's wave equation, which describes the wave-particle duality of the electron, the wavelength is equal to h over p. That is the Broglie's wave equation, and therefore p is equal to, we rearrange this equation to get h over lambda, we can then plug in our values for P into our energy equation. And so Ek is equal to P squared over m, which is equal to h squared over 2m lambda squared. Alright? What do we know about lambda if we're describing the electron as a standing wave? We know that lambda is equal to 2L over L for a standing wave. The fact that we have L means that we have a boundary condition. There's a region of space within which the electron is moving, that this assumption can be correct. And so if we were to plug those values in, we get Ek is equal to h squared over 2m lambda squared, which is equal to h squared over 2m times 2L over n all squared. And that turns out to be equal to Ek is equal to n squared h squared over 8ml squared. Again, I'm just showing you the relationship that that shows how energy is linked to the momentum of the electron and linked to the wave property of the electron. We were able to actually determine the energy of the electron based on the fact that it's a particle moving like a wave, having a particular momentum, having a particular wave form. And we're seeing here that the energy is quantized because we have n in the equation, and also that the energy of the electron is this value only when we have it in a specific region of space. Alright? And that is born through the fact that we have L being the boundary condition here. And so this is basically what this is telling us, that at a specific quantum number, the electron has a wave function which changes based on the sign equation, that it is within a particular region of space, and that there is an associated energy with it. And the energy value is dependent on n and also dependent on L. It's clear that if the electron is at this point, it has a higher if it is at this point, it has a higher value than if it is at this point. It will be 0, and that kind of a thing. Alright? So how does knowing that the electron travels in a wave form, being described through its wave function, having an associated energy, allows us to determine its location? The fact of the matter is that it doesn't really tell us definitively the location. It gives us a sense, it gives us an idea of where the electron is, but because of the uncertainty that it comes with, because it's a wave, because it's described through a wave function, there is an uncertainty that there is in determining the location of the exact location of the electron. Alright, as I said before, for a particular wave function, the location could be here, could be here, could be here, but we have a sense of where it is or where it can be, but we don't know definitively what. And so we need to find or utilize our understanding of what the wave function tells us about the electron's motion, to see if it is that we can get a better picture of where the electron is. Now let's go back to this idea of the interaction of waves. Alright, when two waves interact, we have constructive and destructive interference. Alright, and so if we consider two, and so if we look at it, we can basically say that the resultant wave, right, which gives us a bright intensity or zero intensity, okay, whether it's constructive or destructive, is really the product of two waves. And if the wave is described through its wave function psi, then the product of the wave function, which is psi squared, allows us to get an idea of the intensity caused by the interaction of the waves. Alright? So here we have a situation where if we have constructive interference, then we have a probability of determining where that interaction occurs, or where that wave, resultant wave is. If we have let me see what I'm trying to say here. Alright, so let's go back to what I'm trying to say. So I'm saying that when you have a situation of high intensity, right? High intensity is a product of strong interaction, strong overlap of the waves, right? The product of the waves, or the wave functions, gives rise to high intensity or constructive interference. And so when we look at this image here, the intensity here is very high because you can see it's a tall wave, one, and it's very bright, right? And this indicates to us that there's a high probability of interaction. The parts where you have, if you notice that as we go further out, the rings get less intense and less intense. That's because you have a reduced intensity of the interaction, and that indicates that there's a low probability of interaction. And of course, where there is darkness, right, where we have the red lines, the red areas, that shows where there is destructive interference. The probability, there's zero probability, or zero, the product of the interaction is zero. Alright? And so if we take this analogy of the interaction of light waves and relate it to the diffraction of electrons, right? Where we saw where in a diffraction pattern, from a diffraction pattern where we had diffraction of electrons, we have areas of bright lines, bright bands, bright circles. That is telling us that the waves that cause that constructive interference is from high probability of interaction. All right, and regions where you have dark bands is as a result of low probability of interaction, zero probability of interaction, and regions where you have light or darker light bands, right? As you notice that as you go further and further out, the bands are becoming lighter and lighter, or less intense. The less intensity is as a result of less interaction, or the probability of less interaction. And so if we think of the intensity as related to, or if we think of electrons, a mass of electrons or a bunch of electrons, as a region of electron charge density, alright, then where we have very bright bands, that is indicative of regions of high electron charge density, or high probability of finding or having interaction. And if you're going to have a high probability of having interaction, then you're going to have a high probability of finding the electron. And the opposite occurs where you have darkness, destructive interference, low probability of interaction, zero charge density, zero probability of finding the electron. Regions where you have some amount of intensity, but it is diminished intensity, low intensity, you have low probability density, low electron charge density, and also a low probability of interaction, or low probability of finding the electron. And so the significance, the physical significance of utilizing the wave function, which describes the electron motion, allows us to also relate the interaction of wave functions to give an idea of the probability of finding the electron. So psi squared is essentially allowing us to be able to define in more precise terms a possibility of finding the electron within a particular region of space. Alright, so the wave function of the electron, which is described through this equation, this sine function, allows us to be able to, it basically describes the wave motion, okay, but the square of the wave function allows us to get an idea of the probability of finding the electron in a region of space. And so let us look at it again, go back to our one-dimensional box and correlate wave function with wave function squared. Alright, so here we have wave function, right? For n is equal to 1 we have that, for n is equal to 2 we have that, n is equal to 3 we have that, right? If we were to square the wave function, remember that the wave function is described through this value here now. If we were to square this value, the value of the wave function within this region of space at n is equal to 1 is all positive, Alright, it's above 0. If we were to square that value, it is going to be a bigger value. Alright, which is what we see here. It's a product. If we square this, we see that this becomes maximum. If we square a negative, so if we're squaring the positive, if we have the interaction of these two wave functions, it means that we're squaring them. Alright, and so if they're going to constructively interfere, right, then it means that the product, and by constructive interference we mean that they're going to overlap side by side. They're going to overlap, right, and so the product of their interaction, the product of their overlap, is going to be a positive value, because this is going to be enhanced, and because it's a signed function, if we square a negative, it is going to be positive, and so that's what we're seeing here. Alright, and the same thing obtains when n is equal to 3. Now if we look at this here, we're seeing that now we have a better probability of finding where the electron is, particularly when it's n equals 1. We're able to find out that the probability of finding the electron is the same when we're actually at a quarter of L as also at a 3/4 of L. The probability of finding the electron when it's actually at half of L is 0, and when it's x is equal to 0 and x is equal to L, it's 0. And in the case of n is equal to 3, we're having 3 points at which we can essentially have a very strong probability of finding where the electron is. And so the wave function allows us to be able to determine or describe the wave motion, but the psi square, the product of the wave function, allows us to be able to have a probability of, or determine the probability of finding the electron within a specific region of space. And therefore, this particle in a one-dimensional box, or this electron in a one-dimensional box, can be extended to an electron in a three-dimensional box, which essentially is what describes the atom, because we are talking about the region of space 360 degrees around the atom. And x, y, and z scales, or x, y, and z axes, basically allow us to be able to present a three-dimensional perspective of the region of space. Alright, and so we can also extend the probability density, or the probability of finding the electron in 3 dimensions. And so, how do we visualize a wave function in 3 dimensions? If you go back to look at this picture here, we're seeing 2 different waves essentially spreading out. Alright, the wave starts out at the center, and it's not moving in an x direction or a y direction or a z direction. It's moving in all directions. And so, and if we're saying that the wave can be described through its wave function, the wave function, right, which describes the wave motion, is also a 3-dimensional wave function. Alright, and we can basically look at that using these interpretations here. Here we have a one-dimensional wave function, and we're looking at it when n is equal to 1. We see that we only have one dimension along a particular, say, x or y or z. But if we were to look at it in terms of the 3 dimensions, we see that it still has the same waveform, right? The same shape, but it's spread out over it's spread out over all dimensions, right? It's 3-dimensional. And here is a depiction of what that could look like in terms of concentric circles. The concentric circles are emanating from the center out in all 3 dimensions. That is a 3-dimensional wave function. If we look at n is equal to 2, right? N is equal to 2 is just one line along one axis. It's got one node, or 2 nodes, one in the middle, one at both ends. And if we were to depict that from a 3-dimensional perspective, we're seeing that they have the same waveform, but in terms of 3 dimensions, they go in all direction. Alright? This is positive wave function, and this is negative wave function. Alright? And so, considering the fact that the wave function is 3-dimensional, you can't pinpoint along a particular axis that the electron is likely to be moving. It is moving in all 3 directions, and this shows precisely that the position of the electron is also so uncertain. But by squaring the wave function, you reduce the uncertainty and enhance the probability of finding the electron in a particular region of space, essentially. And so Schrodinger went on to solve the wave function in terms of its energy. That is to say that he went on to link a particular wave function with a specific energy, which is essentially what we want to do, because we want to actually, if we're determining the location of the electron, we need to know what the energy of the electron is. And the wave function, as described by the sine function here, does not relate directly to the energy of the system, except that the energy of the system we know is linked to n and is also linked to L. But Schrodinger went on to propose the Schrodinger wave equation, where he links the wave function psi with the kinetic energy of the electron, which is dependent on the electron moving in all planes, the x, y, z, and z planes, and the potential energy V as well, and the total energy. Alright, so the product of the kinetic energy and the psi function, or the psi function, yeah, plus the product of the potential energy and the psi function is equal to the product of the total energy and the psi function. And this is a Schrodinger wave equation, which basically links directly the wave function and the energy. And a simplified Schrodinger wave equation essentially shows that the wave function can be solved in terms of its energy, which is essentially what we want to be able to do. Alright, and what we see is that because the psi function, or the wave function, is dependent on n, the energy also is dependent on the principal quantum number. And so the idea of quantization shows up because both values of E and psi change when n changes as well. Alright, and this is essentially what the Schrodinger wave equation basically allows us to do. It is a wave equation in terms of the wave function, which predicts precisely the probability of locating the electron, and it solves the wave function for the electron in the atom and relates it to the energy of the electron for a particular distance from the nucleus. Alright, and so let us summarize what we've learned. Again, quite a bit. We basically were introduced to this idea of the wave-particle duality, essentially summing up that all matter, and certainly all small particles, has a wavelength associated with it, and as such exhibiting a wave-particle duality, which is summed up by the de Broglie wave equation, which shows that the lambda wavelength is equal to h over p. And also that there is an uncertainty in determining exactly where the electron is, and therefore this discredits the Bohr's model, because the Bohr's model basically shows that because the electron is traveling in an orbit, one is able to determine exactly where the electron is. But according to Heisenberg uncertainty principle, it is impossible to know both the precise position and momentum of a particle simultaneously, and with any great certainty. Alright? And then we went on to describe because of the wave-particle duality and because of the uncertainty in determining determining precise the position and momentum of the electron, but also linking the wave property with the momentum, or with the particle property, one can then describe, and the fact that the wave property is described as a standing wave, one can then, according to what Schrodinger did, propose that the wave motion of the electron is essentially described by a sine function, which is the wave function of a particle that is moving in a particular region of space, and that this wave function, which describes the motion of the particle, and in this case the electron, is quantized, and it is a three-dimensional property. And the wave function, the value of the wave function is essentially solved and linked directly with that of the energy of the electron, which basically is summed up in the Schrodinger wave equation, which basically links directly the kinetic energy with the wave function, the potential energy with the wave function, and equates those with the total energy of the system. Alright, so for the next session we want to review section 2.4, which basically looks at some of these concepts. You will recognize that much of what I've introduced you to is not in the text. I don't want you to know all of the details. What I want you to recognize are the relationships and how it is that one went about the thought processes that are involved in coming up with these interpretations of where the electron is within the nucleus. Now, you have to know the correlation with wave function and wave function squared, or the probability density, because that is what we're going to be using now. We're going to be looking at what is the physical significance of the psi squared, the probability density, in defining, based on the principal quantum number and the energy of the system, to define specifically the location of the electron around the nucleus in terms of orbitals. Alright? And we're going to show mathematically how it is that we come up with the shapes of orbitals based on the wave function and the square of the wave function. Alright, so in reading ahead, we wanted to read 2.5, and then to explore the concepts of the wave-particle duality using worked example 2.6, and Heisenberg uncertainty principle using worked example 2.7. Okay, see you next time.